Hello, first of all, I hope you are all doing well and staying safe. Today, we are gonna discuss practice assignment 2. So please watch lecture 2 before watching this tutorial. In tutorial 2, we'll discuss two main concepts, which are memory hierarchy and cache. We'll discuss here memory hierarchy. So we have different levels of memory. Hard disk, main memory, cache, registers, which differ in size, speed, and price. So we will start with the registers, which which are the fastest, because they are made of very fast transistors. However, we can't afford big space or size of this disk, um, because the material, uh, which um, which is the material of the transistors, is very expensive compared to the materials of other transistors. Okay, that's why registers are very few in a computer. However, they are very fast. Okay, the second level is the cache, which is slower than the registers but faster than the level below it, which is the main memory, because it's made also of a faster transistors but still slower and cheaper than the registers one. Third level is the main memory, where it is slower than the cache and bigger in size and less expensive as well, but it is faster and smaller than the hard disk. So, as we see here in the figure, as we go down the pyramid in the levels, the size increases. However, as we go up, the size decreases. This is for the size. But for the speed, as we go up, the speed increases. So the registers are the fastest, then the cache, then the main memory, and so on. Why do the size and um, the speed differs? Because of a main factor, which is the price. Because the registers are very expensive, and the material which it is fabricated from is very expensive compared to the cache, compared to the main memory, and so on. So that's why we have the idea of levels. They can differ in size and differ in speed. The idea of levels here is that we store the most important data near the processors for fast access. Why there is fast access? Because the material that the registers and the cache are fabricated from are faster from the memory, and so on. And if we want as big registers as big as the main memory, it will cost much money. We can't afford, so that's why we decide to have levels where the access is faster. We start with question 1. Consider a direct math cache of 8 blocks. Table 1 shows memory references by the processor. Complete table 1. How many states of the cache are there? What triggers a new state? Complete table 2 reflecting the cache's final state after the series of references in table 1. So we need first to understand what is cache to understand this question. Cache is an intermediate memory level between processor and the main memory. Okay, so we know now it's an intermediate level between the memory and the processor. We need to know, why do we need cache? Because accessing the main memory causes much delay. Why? Because the main memory is big in size and searching in it causes much delay. Moreover, the hardware nature of the main memory is slow. That's why cache is used to store important data that is accessed frequently by the processor. So instead of going to the main memory, I can get it fast from the cache. Why we choose the cache? Because the cache has smaller size and faster hardware. So when we search for the data, the access of it is much faster. So we have less access time. However, since the cache is smaller than the memory, we can't fit all the data we want in the cache. So that the data in the cache should be mapped one way or another to the main memory. There are many ways to do the mapping between the main memory and the cache. So again, why do we need to map between the main memory and the cache? Because the main memory is very big compared to the size of the cache, and we want the processor to deal with the cache and access it instead of accessing the memory. So if I want a certain address from the memory, I request it from the cache, and the cache should have it. So, but we can't fit all the data in the main memory in the cache due to the difference in size, and that's why the mapping happens. We want to map between the main memory and the cache. So when I'm accessing an address from the cache, it should go to the main memory with the correct address to get the correct data. And that's why the mapping happens. And we will discuss in this problem one way of this mapping, which is called direct mapped cache. So in table 2, on the right side of the slide, we see here how direct map cache looks like. This is a cache of 8 blocks, so we have 3 bits to represent the index because we have 8 different values. So log 2 to the log 2 to the base 2 for 8 is 3. So we have 3 bits here. So we know which block caches in reading or writing. If I want to read or write from the cache, I need to know which block to go to. Okay, so there's the index, which is the 3 bits, which is just like the number of the block I am in, and we have here the valid bit, which is a type of flag indicating if this block is used or not. So if this block is not used, which we have here in this case because we didn't use the cache yet, it is no. And if this cell in the cache is used, the valid bit is changed to yes. The tag field is the remaining of the address. So what the remaining means, if you have an address of 32 bits and we want to access this address from the cache, we have 3 bits for the index and the remaining is considered the tag field. So if we have an address of 32 bits, 3 bits are taken for the index, and 29 bits are taken for the tag. The data field is the data stored in the address. So when the memory when I want a certain data from the memory, the cache gets it and puts it in that data field, and that's why we have here the data in the cache. In this problem, we want to access the following addresses in the left table, and we want to know if this is a miss or a hit, as well as filling the cache table in the right. Another thing is how we can determine if this is a hit or a miss. First, we have the input address, and we divide it into an index, tag, and then we take the index port and checks the index block in the cache. If the valid bit for this index is true and the index and the tag is equal to the tag we have, then this is a hit. If the valid is not true, then it's a miss. If the valid bit is true and the tag is not matching the tag, then it is also a miss. So the only case of the hit is that if the valid bit is yes and the tag is equal to the tag. So this is the current state of the cache after the processor missed the address 22. Therefore, it got the data from the main memory and write it in the cache. So if the data is needed again, the processor can find it in the cache already. Here we find that the index of block uh, the block with the index 110 have the tag port and the valid is turned to yes, and the data port is filled with the data from the memory with this address. For the address 26, it's similar to the previous one. We first convert it into binary. So the number is 11010. Since the index is 3 bits, we take the least 3 significant bits from the address, which is 010. Therefore, we go to block number 010 and check the first valid bit. And we will find that the valid bit is no. So that means there is no data in this block, which means this is a miss, as it appears in the first table. Now we should update the cache and put the data we missed, because after the miss happens, the cache retrieves the data from the main memory and updates the data in the cache. So this is the state of the cache in the lower table after the processor missed the address 26 and got the data from the memory and put it in the cache. Therefore, if we got the data from the main memory and we want to retrieve this address again, we will find the data already in the cache and it will be considered as a hit. For the address 22, we first convert it to binary as usual, which is 10110. Since the index is 3 bits, we take the 3 least significant bits from the address, which is 110. Therefore, we got 110 block and we check the valid bit first. We'll find the valid bit is yes. So that means there is some kind of data in this block. Now we want to make sure that this data is the data we wanted or the processor is requesting. So we compare the tag, which is 10. We check the tag, the 10 with the 10, we'll find them matching. So that means we are having here a hit. Now we don't have to update anything in the cache or do any more modifications to it, since the data we wanted is already in the cache. So no update in the data, and here we see in our table, which is the first one, that the 22 we got a hit since the tag is equal to the tag and the valid bit was true. Similar to the previous address, here we have 26, which is a repetition of an address we tried to retrieve before. So of course we will find the data in the cache, since no further modifications happens in the same field. So here for 26 we will go to block 010, which is the index, and we find it that the valid bit is already yes, and we will find the tag is equal to the tag, which is 11. So we can now retrieve the data directly from the cache and no need to go to the main memory, causing this to be also a hit. For the address 16, we first converted as usual to binary, which is 10000. Since the index is 3 bits, we take the 3 least significant bits from the right from the address, okay, which is 000. Therefore, we take this index and go with it to the cache into block 000, and first we check the valid bit. We will find that the valid bit is no, so that means there is no data in the block. So the data we want is not here, which means this is considered as a miss, as appears in the table above. Now our job is not finished yet, or the cache job is not finished yet, as it has to retrieve the data from the main memory. So it goes to the main memory with the address given, which is 16, and get the data from it and writes it into the cache. So if we get the data from the main memory, now if you want to retrieve this data again, we will find the data already in the cache, which is the main job of the cache, as we explained before. For the next address, which is 3, we first convert it into binary as usual, which is 00011. So we take the 3 least significant bits to take the index, which is 011. We now go to block 011 from the cache. We will check first the valid bit. We will find it no. So that means there is no data in the cache in this block, which means that this is considered as a miss, uh, and we put it in the table above. So after that, we insert the data into the cache, similar to what we did before in the previous addresses, and we put the tag, we put the data in the cache um, for retrieving it after that. The next address is 16. Even if it's clear that we already used address 16, we have to make sure that this is a hit using the algorithm we learned. So we convert it first into binary, take the 3 bits for the index, go to the cache, compare the check the valid bit, compare to the tag, and then if all these conditions are true, we consider it as a hit, and we don't do any update in the cache since the new data or the no modifications in the data is needed. And this is the case here because 16 is considered a hit because we find the data in the cache. Now we have address 18, which is an important one because it has a new concept. We've of course converted into binary, which is 10010. We take the least 3 significant bits, which is 010, and then we go to block 010 in the cache. We will find that the valid bit is yes. That means there is some sort of data in this block. Now we need to check if this data is the data we want or not. How we do that is by comparing the tag. So the tag here is 10. We compare it with the tag that is already in the cache, which is 11. We will find that they are not matching, which means that this is considered a miss. So now we have the valid bit is yes, but the tag is not equal to the tag we have because this data is different to this data because there are two different addresses. Okay, that's why it is considered as a miss. Now we should update the cache and put the data we missed because after the miss happens, the cache retrieves the data from the main memory and updates it in the cache. So this is the state of the cache after the processor missed the address 18 in the table down. This is done by replacing the old data in the cache by the new one of address 18. As we see, there were data from a previous address we used before, and now we replaced it by the address we have. So we keep the most recently used data uh, in the cache. Therefore, if we get um, an address with the same index of address 18, we will find the data um, stored in the cache of address 18. The final address is address 16 again, and now should be easy and we should know how to do it. So similar to the previous uh, addresses, we follow the same algorithm and take the index, first convert it into binary, take the index and compare the valid and first check with the valid bit and compare the tag. We'll find that address 16 We already did it before, and we did no modification to the block 000, and that means that this is a hit. If we want here to calculate the hit rate or the miss rate, we should get the total number of misses over the total number of accesses. So now here we have uh, 1, 2, 3, 4, 5, 6, 7, 8, 9. We try to access the memory 9 times. We have here 4 hits and 5 misses. So the miss rate is 5 over 9 and the hit rate is 4 over 9. Okay, this is how we get the miss rate or the hit rate. So, question 2. Consider a cache with 64 blocks, a block size of 16 bytes. To what block number does byte address 1200 map in cache? What other byte addresses are mapped to this block number? In order to understand this question, we need to read it slowly and try to draw it. So here we have a cache of 64 blocks. So as we have before in the first question, we're having a cache of 8 blocks. Now we have a cache of 64 blocks. So we have from block number 0 till block number 63 as shown in this figure. Okay, and in each block we have 16 bytes. So we have from byte 0 till byte 15 in the first block, and in the second block we have from byte number 16 till byte number 32 and so on. Okay, what does the question need? It needs that to know where does byte 1200 map in this cache. So it's simple. If we have 64 blocks, each block has 16 bytes. If we want to know the byte number, easy math calculation, we divide the address we have by 16. If we do that, it will tell us to what block does the address 1200 belong. So if we divide it 1200 with 16, we will have 75. So the address 1200 belongs to um, block number 75. Here we have a problem. What is the problem? Is that we don't have block number 75. We have from 0 till 63. So there is no block number 75. What do? We have to think how memory works. Memory works at whenever we have an address that exceeds our limit, it goes from the beginning again. So if we have address number 75, what will happen? When it finishes the whole 64 blocks, it will go from block 0 again and start all over. How we can get uh, the 75 mapped to the 64 blocks? Easy. We can do a modulus calculation. So 75 modulus 64, it will give us 11, where 11 is a block number that address 1200 belongs. Okay, we can do it in an easier way when we have the 75 and we know that the memory or the cache will start all over. We will just subtract the 75 from the 64 blocks we have. We will have block number 11, which is similar. Okay, we will get the same answer. So again, to understand the figure we are having here a cache, and we are neglecting the index and the tag port and the valid bit. We're just having here the data port. So we have a data of 64 blocks, each block having 16 bytes, and we want to know the byte number 1200. So we need to know, um, if for example, if you are searching for another address, which is address, for example, 25. How we know it? If we have in block 1 addresses from byte 0 till byte 15, and in block 2 we have from uh, 16 till 32, then it belongs to block 2. But we don't have a number we can calculate easily, so we need to do the calculations. How we do it? We divide by 16 to know to which block number this address belongs. We found out that it is 75, which is a number we don't have because we only have 64 blocks. So that's why we did the modulus to know, um, to which block does address 1200 belongs. Okay. The other question is, what other byte addresses are mapped to this block? So this is an easy question. If you have the address 1200, um, it means that this is the beginning of a block. So easy. We add 15 to it to know the range of addresses, which is from um, 100, 1200 till 100 2050. Um, if we find if you find that it's not clear, let's have an easier example. So here, block 0, we have blocks from 0 till 15. In block 1 we have addresses from 16 till 31, and so on. So so block number 75, we have from 1200 till 1250. Moving to the next question. Suppose we have a processor with a base CPI of 1 and a clock rate of 4 GHz. Assume a main memory access time of 100 nanoseconds, including the mishandling. Suppose the miss rate per instruction and the primary cache is 2%. How much faster will the processor be if we add a secondary cache that has a 5 nanosecond access time for either a hit or a miss? And is Doge enough to reduce the miss rate to the main memory to 0.5%? In order to answer this question, we need to understand it first. Okay, so we are having here two cases. The first case, we are having a main memory and a primary cache or only one cache. So when the processor needs data, it requests it from um, the cache. If the cache finds it, it go back to the processor with the data. But if it misses, it goes to the main memory, access it, and take the data from the memory and go back to the processor. Okay. But do we have to go to the main memory every time? No, because we miss was only 2% in the primary cache. Um, so for example, if you are having 100 times accessing the memory, we will miss only 2 times and we will hit 98 times. Okay, so if we have only one instruction, we will miss with a rate 0.02 for this instructions. Okay, and here we have the access time of the main memory is 100 nanoseconds. What does the 100 nanoseconds represent? It represents that this is the time taken to take or to access something from the memory. This is a property of the main memory itself. So if I'm taking anything from the memory, any module is taking any data from the memory, it will take 100 nanoseconds. Okay, this is the first case. The second case, we are having here two levels of cache. So we add another cache between the first cache and the memory. So when the processor needs data, it goes to the cache, the first cache we had before, and if it finds the data, it go back to with the data to the processor. If it doesn't find this data, it goes first to cache 2 and checks if the data is in cache 2. If it is in cache 2, it goes back to cache 1, and then from cache 1 to the processor. But what if the data is not in the first cache or the second cache? It will go to the main memory to access it, causing the delay of the 100 nanoseconds of access time. Okay, but we have here, since we will access the second cache as well, we have an access time of only 5 nanoseconds, and the miss rate between the cache 2 and the main memory will be 0.5% only, which is 0.005. So every 100 instructions, we only have or 100 times accessing the memory, we only have 0.5 um, 0.5 misses. Okay, so here we are having an average calculation, because there's nothing called 0.5 misses or 1.7 misses. This is an average calculation for the number of misses we have when we are accessing the cache or the memory or whatever module we are having. Okay, we will explain each case, and we will try to calculate the total CPI for each one and compare them together to know if adding the cache, another cache, that is the second level of cache, will cause a speed up in the performance of this computer or not. So here in the first case, we're having a processor communicating with the primary cache, which is dealing with the main memory. So first we need to put the attributes for each module. We have here the access time of the main memory, which is equal to 100 nanoseconds. But we need to convert this into cycles, because we need to have the average CPI for the first case and the second case. So in order to convert from nanoseconds to cycles, we need to multiply by the processor's frequency, which is 4 gigahertz. So by multiplication, we get 400 cycles. We here need also to understand what is base CPI. Base CPI is the number of clock cycles taken by the processor to access something from, or some sort of data from, the cache, and finding it in the cache without the need to go to the main memory. So this is like the perfect case scenario, when the processor goes to the cache and finds the data in the cache. Okay, this is what is meant by one cycle, base CPI. So if you have 100 cycles or 100 instructions, they will at least consume 100 clock cycles, because each instruction will at least have the base CPI. Okay, this is for the base CPI. You also have another attribute, which is the 2% miss. What is the 2% miss? It is the rate of the primary cache missing from the main memory. What does that mean? If the processor needs some sort of data from the primary cache, it will go to the primary cache. If it finds it, then it's a hit and there's no problem. If the primary cache doesn't have the data the processor needs, we need to go to the main memory. So we go to the main memory only in case of misses only. Okay, but if we hit the data we want in the primary cache, there is no need to go to the main memory. Okay, how frequent do we go to the main memory when we don't find the data in the primary cache? This is the 2% miss rate that is an attribute for the primary cache here. For example, if the processor needs to access the 100 times the data, it goes 100 times to the primary cache. The primary cache will hit 98 times, and will miss only 2 times and go to the main memory. What if we have 50 instructions? We will have only one miss. What if we have uh, much more instructions or less instructions? We will miss by the rate of 2%. So if we have only one instruction, the misses will be 0.02. Okay, this is for one instruction. So we have here a processor of 4 gigahertz. We have a primary cache with a 2% miss rate. We have a main memory where the access time of it is 400 cycles or 100 nanoseconds. Okay, and we have the base CPI of the primary cache with 1 cycle. So what do we need here? We need to calculate the average number of the number of cycles for one instruction only. So what do we need to know? We need to know for one instruction how many cycles it can do. So we have first the base CPI, which is the perfect case if we find the data. But we probably doesn't find the data. So what we do if we don't find the data? If we don't find the data, we will miss. So how frequently can we miss? It's the 2%. So but what is the cost of one miss? The cost of one miss is 400 cycles. So here the total number of cycles is the 2% multiplied by the 400 cycles, which is the cost of the average for one instruction. So if one instruction will miss by 2% and each miss costs 400, and then we multiply both together, getting the cost of the miss for one instruction plus the base CPI. So here we have the equation down. We have 1, which is the base CPI, added by the quotient of the multiplication of the miss rate by the cost of one miss or the access time of the main memory. So we have here 9 cycles uh, delay for case 1. Okay, and in the next slide we will investigate case 2 and compare the two cases together. In the second case, we have a processor, primary cache as the last one, but we here added a secondary cache between the primary cache and the main memory as shown in the figure. Okay, what are the extra attributes we have here? We have um, the same access time of the main memory, which is 400 cycles, but we have here an access time also for the secondary cache. Why we have an access time for the secondary cache? Because the primary cache will try to access it if the data is not found in the primary cache. So how many clock cycles does the secondary cache consume when accessing it? We have as access time of 5 nanoseconds. So in order to calculate the number of cycles for this axis, we multiply the 5 nanoseconds by the frequency, which is 4 gigahertz. So we have here 20 cycles access time for the secondary cache. And we have 0.5 miss rate if we missed at the primary cache, and the secondary cache misses, it misses by a rate of 0.5 misses, and the rest of the attributes are the same from case 1. So what we have here is that we are having 3 ports. The first port is between the processor and the primary cache. The second port is between the primary cache and the secondary cache, and last but not least is the port between the secondary cache and the main memory. So, of course, the things that consumes uh, most time or the biggest delay is when we are accessing the main memory, and the less is the secondary cache and less is the primary cache. The first port is between the processor and the primary cache. We have here only one clock cycle. Why one clock cycle? Because the base CPI is one cycle. And as we mentioned before, the base CPI is the time or the number of cycles taken by the processor to access the data from the primary cache and get from it. This is the first part. The second part is when the primary cache doesn't have the data that the processor wants, it will have to go to the secondary cache. How many times or with what rate will this happen? It will happen with a rate of 2%, which is the miss rate of the primary cache, which is 0.02. Okay, and how much clock cycles does accessing the secondary cache consumes? It consumes 20 cycles. So we are having here, if we will access the secondary cache only one time, we will have 20 cycles as a cost. But we will not access it 20 time, one time. We'll access it only 2%, which is 0.02. This is the second port. Well, the third port is a port where we don't find the data in the primary cache, neither is the secondary cache. So we will have to go to the main memory, which is having all the data, which this port, as we mentioned before, is the one that costs the most of cycles or the most of the delay. Okay, so the one accessing to the main memory costs 400 cycles, but at which rate are we going from the secondary cache to the main memory? Yes, it's only 0.5 misses, which is an input in the question. So we are having now all the attributes. In order to calculate the average CPI for case 2, we will have to add the three cases together. Okay, so for one instruction only. So for one instruction, we will have only one base CPI, and we will access and we have a probability of 2% missing from the primary cache going to the secondary cache, and going to the secondary cache costs 20 cycles. That's why we will have 2% multiplied by the 20. This is the second part, but we also have a probability of missing at the secondary cache, and when we miss at the secondary cache, we have to access the main memory. Accessing the main memory costs 400 cycles, and this 400 cycles has to be multiplied by the rate of going to the main memory, which is 0.05%. If we add the three values together, we will have here 3.4 cycles. Okay. In case 1, the total CPI was 9 cycles. In this case, we have 3.4 cycles. So if we want to know the speed up of case 2 from case 1, we have to divide the average CPI or the total CPI for one instruction for case 2 and case 1, which is 9 over 3.4, which is 2.64. This is the speed up. It is 2.64 faster than case 1. Here we should notice that adding an extra hardware will cause a speed up in the performance of our computer, since we are reducing going to the main memory, because the main memory, as we mentioned before, is very slow. So we try to decrease accessing the main memory. This is all for practice assignment 2. If you have any questions, please don't hesitate to send us on Piazza your questions, and we will answer it as soon as possible. Thank you and stay safe.